All right, folks, let's go ahead and let's pick up where we left off with yesterday. No new announcements today, but looks like more of you were able to finish on time yesterday, so that's good. I'm going to try to keep the videos at around the same time. I'm recording myself, so I'm timing myself, so I'm hoping that I can keep the videos right around 20, 25 minutes in order for you to be able to get the rest of the work done and get your paper filled out and then uploaded to Classroom. Okay. All right. So let's go ahead then. And what I'd like you to do then is let's start with number two in your problem set here. Let's go ahead. Let's name these compounds. Remember, naming the compounds are important, but I think more important for us in the immediate future here when we go over it, that you need to be able to get these formulas. If I give you the names of the compound, you have to get the correct formulas, folks. If you don't, it's going to be very difficult for you moving forward with what we do. So let's practice this. Take about a couple minutes to fill in as many of these as you can. I'll give you the answers, okay, and make sure you write these down, your answers and my solutions for you on your paper, and that way then you'll have the correct answer to study from. Okay. All right. So take about a couple minutes to get the answers to the name these compounds. Okay. All right, let's go ahead and let's take a look at these compounds here, and let's take a look at their names. Okay, so hopefully you recognize, be able to identify the types of compounds as well, meaning then make sure you can identify if they are molecular, covalent bonded, or ionic compounds, or ionic bonded. Make sure you're able to do that and be able to get that done. Okay, so let's go ahead and let's take a look at the first one here. I'm going to change the pin code quickly here. Okay. So hopefully you're recognizing that this first compound here is a molecular compound. And so since it's a molecular compound, we use the prefixes to name this compound. So this very first compound then, xenon, we only have one of those. We do not need to include the prefix mono for the very first element in the compound. Okay. And then we have then four fluorines, so it's going to be tetra. And remember, with these here, we want to make sure then that with the ending, we drop the ending, we add IED. So this is going to be xenon tetrafluoride. Okay. The next compound then is an ionic compound, metal and a non-metal. And so we just name the cation, we name the anion. This is about, if you notice, all of these are binary compounds. Binary because it's made up of two elements. Okay. All right, so with that said, then the second one is going to be aluminum. That's the name of the cation, the aluminum cation. And the anion then is going to be sulfide. Remember with this also, you drop the ending and add IDE. Okay, so sulfide, no Roman numeral here because aluminum is not a transition metal. However, with the second ionic compound, and again, this is also ionic because you have a metal and a non-metal. This time though, your metal is a transition metal, so we have to indicate the charge on this transition metal by writing the Roman numeral in parentheses. This is cobalt 2. If you're not quite sure how we get that Roman numeral 2, folks, make sure you drop by after school today with our Zoom classroom, and I'll explain to you. We'll be live at that point, and I'll explain to you how we get that Roman numeral 2. Okay. All right, the fourth compound down, also ionic, but here again, this is a representative metal, so we do not need to write down the Roman numeral. So this compound then is calcium iodide. Okay. Next one, also an ionic compound. This is a representative metal, but remember, this is one of the four representative metals where you have to include a Roman numeral. So make sure, again, if you don't remember what those four are, you come by after school and you get that help. This is going to be then tin 2 chloride. So folks, make sure you write down these answers on your paper for submission afterwards. Okay? All right, so here we have a molecular compound, two nonmetals, then we have selenium oxide. Okay. Next one, also a molecular compound. So remember, you could include here mono oxide, but you'll find that in a lot of texts and a lot of books with oxides here, for example, fluorides with the halogens, they leave off the prefix mono. And so you can also call this selenium monoxide, but you'll see it as selenium oxide. Okay. All right, so we have the next one. It's an ionic molecular compound again. And so we have then iodine. Okay, and 5 fluorides, so it's going to be penta fluoride. Okay. And the last one, we have then another ionic compound. Zinc is a transition metal, but remember zinc, I told you already, has only one charge that we need to worry about, which is a +2. So you don't really technically need that Roman numeral here, so I won't include it. So therefore, the name of this compound then is going to be zinc chloride. So if you include the Roman numeral 2 here, in terms of convention, it will be wrong, but I won't mark you off for it because I did tell you when we learned this back in chapter 7 and chapter 9 that I want you to get in the habit of using those Roman numerals. So go ahead and use the Roman numeral as well. Okay. All right. So those are the answers for the problem here. Please make sure you write it down on your sheet and then turn it in at the end of the lecture. Okay. All right. We left off at the discussion of the mole. We said then that the mole is a unit that we can use to describe how many particles we have. And so we said then a mole, when we define the unit mole, that mole is equal to this many, 6.02 times 10 to the 23rd particles. Good. And what we need to make sure to remember, these particles here, these particles are the atoms that we have to deal with, the molecules, the formula units, basically very small formula units, the very small particles that we have to deal with. Okay, and so we can use this then as a conversion factor because we're saying that these two quantities are exactly equal. We can use the conversion factor here to solve for a problem like this. And so we solved for a problem like this, very similar problem like this yesterday. So what I would like you to do is take about a minute or so to work out this problem, and then do the best you can with it. Refer back to number 16 that we did yesterday, and use that to help you. And then once you get back, I'll go ahead and work out this problem for you. Okay, so take about a couple of minutes to work out this problem. Okay, let's go ahead and remember, this is a conversion problem, so we want to identify what we start with, what they give us to start with, what they ask us to solve for, and then our conversion factor. Okay, so here we have this. We are told then we have 1.75 moles of this particular compound made of 1 carbon, 1 hydrogen, 3 chlorines. They're asking us to find the number of atoms. So make sure you keep that in mind. We start with this here. This is what we start with. And this is what they want us to end with. So that's the end unit. Okay, so make sure you keep this in mind. The end unit is atoms, okay, not number of particles. Okay. All right, and so with that said, then we have our conversion factor here. We've identified all three of them. Let's go ahead and work this out. Okay. So we start out with then 1.75. Okay, we have moles of CHCl3. We want to find then the total number of atoms. The end unit here is atoms, and so make sure you keep that in mind. Okay. All right, so we have, let's go ahead and use this one here. So the first conversion factor that we're going to need then is going to be 1 mole. And what I would suggest you do is write in the particle that is being referred to. The particle here is CHCl3. So 1 mole of CHCl3 is equal to 6.02 times 10 to the 23rd. And again, the particle here will also be CHCl3. So these particles have to be the same. Okay. All right, so if you take a look at this, if this is the only equivalent we're going to use to carry out our conversion, this unit will be taken care of, but we don't have this unit included. And so we need a second conversion factor in order to get that done. And that second conversion factor will relate how many atoms are in a single molecule of CHCl3. And if you count the atoms here, you have 3 chlorines, 1 hydrogen, 1 carbon. We're going to have 5 atoms. So that's the second equivalence that we can use in order to carry out this conversion. Okay. All right, so let's go ahead then. So there's atoms right here. That'll take care of this unit. There's moles of CHCl3. That'll take care of this unit. So let's go ahead and start plugging it in and see what we get here. Okay. So hopefully you recognize that we're going to use this one first, and we're going to put Avogadro's number on top, 6.02 times 10 to the 23rd. The particle here is CHCl3. That's going to be over 1 mole of C. Sorry. Hold on a second. Let me get back in here. Okay. Sorry about this, folks. Okay. CHCl3. The reason why we have that there is that this allows us to cancel out this unit here. So we take care of that unit with the first conversion factor here. Once we've used that conversion factor, folks, remember, don't go back and use that one. Okay. And so we're going to plug in the second one now in order to get our unit here. So with that said, then we have CHCl3 on the top here. We need to have that on the bottom in our second conversion factor. And then 5 atoms on top. Okay. If you do it that way, that unit cancels out. We end up with atoms on top. The analysis, the dimensional analysis done. You just need to plug in your numbers now. And again, make sure you use your calculator in order to get this done. Again, I didn't see anyone come by yesterday to get that extra help. So come by our Zoom classroom today after school, 3:15 to 4:15, if you're having trouble with your calculator. Okay, so you plug those numbers into your calculator, you'll end up with an answer that is 5.27 times 10 to the 24th atoms. Okay, and that will be your answer. Okay. All right. So make sure you write that down onto your paper, and make sure you have that turned in. Okay. All right. So with that said, then we know now what we can do, what the unit mole is. We know now what we can do with that unit mole. The only problem that we have here then is that we don't have any measuring devices that measure in units of moles. We want to be able to measure out these substances. And the way we do that is that we have to be able to determine the masses of these substances. We have to be able to determine the volumes of these substances. Okay, so what we can do then is we have to be able to come up with a way to convert the unit moles into mass. So that's what we're going to talk about next year, and we'll finish up here. So we know then, we already talked about this. I told you the mole of marbles. So I already mentioned this to you yesterday. The mole of marbles is a huge number of marbles. So much so, if we had that many marbles, it would fill this earth to a depth of 50 miles, every part of this earth, 50 miles with marbles. Okay, so that's the mole of marbles. If we could actually weigh out that many marbles, okay, and get a mass from it. Now, make sure you understand this though. The mass that we're going to obtain here, the mass of 1 mole of marble, and I'm just go ahead and write this down for you. Okay, so we had 1 mole of marbles. So we had 1 mole, and if our substance here is marbles, we have 1 mole of marbles. Remember, that's going to be equal to 6.02 times 10 to the 23rd marbles. So a lot of marbles, folks. You get 50 miles deep. Okay. If we had a scale big enough, and if we could weigh all those marbles in, then 6.02 times 10 to the 23rd marbles would have a mass equal to, and I'll write this down for you. Okay. And that's assuming then that each marble is roughly about a gram, a kilogram, about 1,000 grams. And this is obviously overestimating, but 1,000 grams each. Okay. The mass then is going to be 6.02 times 10 to the 20th kilograms. And the assumption here, just to make it simple, then is the mass of 1 marble. And you can do the math here, is equal to 1,000 grams. So it's obviously it is not, but just for the sake of argument, we can use that number there to help us out. Okay. All right. So therefore, 1 mole of marbles, if you can follow this logic here, if we have that many particles, that many marbles in 1 mole, that many marbles has that mass. 1 mole of marbles then is going to be equal to 6.02 times 10 to the 20th kilograms. Okay, again, assuming that the 1 marble is equal to 1,000 grams. Okay. All right, so that's a really huge number. That's a big number, folks. And so it kind of put things into perspective then. If we the mass of the sun is approximately 2.0 times 10 to the 30th kilograms. The mass of the Earth is about 6.0 times 10 to the 24th kilograms, and the mass of the moon is about 7.0 times 10 to the 22nd kilograms. Okay. All right, so this is a big mass, folks. The mass of that many marbles, that's a huge mass. Now, again, obviously, marbles will not be 1,000 grams. Marbles probably be about a gram, 2 grams each. But I just chose this number here to keep things simple for us. And then you can compare the masses here, okay, to the mass that I've given you here. So a mass of marbles is very, very large. Okay? But we can do that. If we know the mass of a single marble, if we know the mass of a single marble, we can determine the mass of Avogadro's number of those marbles. And from that, then we can determine then the moles, the mass of 1 mole of marbles. Okay? So what I'd like to do then, let's take a look at an example. I mean, we don't want to deal with marbles, like I said, but we do with the unit moles. We use that, we apply it to elements, representative particles. Okay? And so let's go ahead then, and I'll work out a problem for you in just a moment that allows you to see that. Okay, so there it is. So if we assume then that the mass of the marble is about 1 gram, we have then 6.02 to the 10 to the 23rd grams, which gives us 6.02 to the 10 to the 20th kilograms. Okay, all right. And so what we want to do is we want to be able to do the same thing for substances, for elements, for molecules, for compounds, okay, so and so forth. And so remember, we had a way to measure or a way to determine the masses of individual atoms. Remember, we took the average atomic mass. This is back in chapter 5. We took the average atomic masses of each one of the atoms, each one of the isotopes of the atoms, and then we were able to obtain this average mass here that's included in the periodic table. And remember, these are weighted averages, and they were measured, they were calculated for, and they were assigned the unit atomic mass unit. Okay, and so with that said, then I'll see you in this moment that if there is a very convenient way, a simple way that we can convert the unit moles into grams. Okay, and I'm going to point that out to you. That'll make life very easy for us. Okay, and so with that said, then when we work that out, you're going to notice then that the atomic masses, the atomic masses that are given to us on the periodic table, correspond directly to this molar mass, that is the mass of 1 mole of each one of those elements on the periodic table. So if you take a look at the periodic table here, let's just take a look at hydrogen as an example. If you take a look at hydrogen, this, remember, is the atomic mass of the hydrogen atom. And so therefore, that we were saying that the 1 hydrogen atom has a mass. So 1 hydrogen atom has a mass of roughly 1.01, and the units here are AMUs. What you're going to see in just a moment is if we had 1 mole of hydrogen atoms, that mass of that many hydrogen atoms will also correspond to this number here, 1.01, but the units now will be grams per mole. Okay, and so this is what we refer to right here as the molar mass, and this is the atomic mass. And that's the nice thing about science and in general, folks, is that we end up seeing a lot of these patterns here that we can take advantage of. And so the numbers here are given to us on the periodic table. These numbers here, for example, this atomic mass from boron also corresponds to its molar mass as well. Okay, so the masses listed here on the periodic table corresponds to what we call the molar mass, and I'm going to be referring to this term a lot more, and I'll go over it with you in just a moment. Molar mass of these elements. Okay, so you can get that directly from the periodic table. All right, so what I'd like you to do then, I want you to work out this problem here, and I want to use this problem here to show you then how the atomic mass of the element corresponds to the mass of 1 mole of that element, which is what we call the molar mass. So real quick, what I'd like you to do with this problem here, just answer the question, do the conversion, make sure you use dimensional analysis, and then I'll use this problem here also to show you how we can obtain the molar mass as well. Okay, all right, take about a couple minutes to work out this problem. Okay, hopefully you had a chance to work out this problem. Let's take a look at it. Let's work this one out together. Okay, let me go ahead real quick here. Sorry, I'm gonna sorry guys. I want to go ahead and put in a slide here that we can use so I can work out the problem for you. sorry. Okay, let's go ahead and let's take a look at this problem here and let's work this out together. So first of all, let's go ahead. Sorry. Yeah, more technical issues. Even online, we have technical issues. Sorry about that. Yeah, let's go ahead and try this again. Okay, there it is. Okay. All right, so we were told that we have 9. So let's work this one out together really quickly. Yeah, we start out then with 9.0. So let me go ahead and write this down. We were told that we have 9.0, 3 times 10 to the 24th. And this is, we're starting out with atoms of mercury. Okay, so we're starting out with individual atoms of mercury. That's what we have. We're going to go ahead and convert that. We want to convert that into moles of mercury. Okay, and so that's what we want to end up with. And so our conversion factor that we're going to use then is 1 mole of mercury. It's going to correspond to 6.02 times 10 to the 23rd atoms of mercury. Plugging that in, we're going to plug it in with 1 mole of mercury on top and 6.02 times 10 to the 23rd atoms of mercury on the bottom, Avogadro's number on the bottom. We're going to end up here then with 15 moles of mercury. Okay, and that's what we have right there. Now, 15 moles of mercury, and I would just want to ask, so that's the moles of mercury. What I would like you to do then is let's go ahead then, and I'm going to do a quick conversion for you. Okay. And to show you then what we'll be doing in just a moment. What we need to be able to do is be able to take the moles of the mercury here and convert it to grams of mercury. Okay. All right, so if you go to the periodic table, you're going to see then that the mass of mercury is 201 grams per mole. That is the number. The 201 is the number that we get from the periodic table. Okay, and that was our atomic mass, but this also represents what we call the molar mass. Okay, and what this molar mass is telling us is then that if you had 1 mole of mercury, okay, that would be equal to 201 grams of mercury. So if you were able to measure out 1 mole of mercury, which is 6.02 times 10 to the 23rd atoms of mercury, it would have a mass of 201 grams. And if you drop it on a scale, that's what it will read. Okay? So if this is an equality here, you can only imagine that what we can do with it. We can use it as a conversion factor then to go from moles to mass here of mercury. So let's go ahead and plug that in. We'll put 201 grams of mercury on the top. Okay, 1 mole of mercury on the bottom. Hopefully you see why we have to do that. If we do that, moles of mercury cancels out. And then when you plug that in, then you will get then the mass here of 3.02 or 302 times 10 to the second, or 302 grams of mercury. Okay. All right, so that's what we can do. This is what we call the molar mass. The molar mass then provides us with this information. It defines for us the mass of 1 mole of an atom, of an element. Okay. We can do the math here to show them what the mass of 1 atom is going to be. If you're interested in that, come on by and see me after school today to get that extra help. But this is what we can do with the molar mass. Okay. So for molar mass of an element, like I told you, we can define that then as the mass of 1 mole of the element, and that number is taken directly from the periodic table. Okay. All right, I think that's pretty straightforward. Okay, so you can imagine then for hydrogen, for example, the molar mass of hydrogen would be 1 gram per mole. The molar mass of helium would be then 4 grams per mole roughly. And I would suggest that with the molar masses, from the periodic table. I would suggest you just round those mass numbers to the nearest whole number to make things a little bit simpler. Okay, all right. So let's go ahead then. We saw, and I want to point this out to you, we saw then that the mass, the molar mass of hydrogen is going to be 1 from the periodic table, 1 gram per mole. Okay, so I'm sorry, I'm running. Okay, that would be good. All right, so that tells me that I'm running a little low on time. I'll continue this here just for about 5 more minutes, okay, and then I'll finish up here. But remember, hydrogen does not exist as a monatomic element. It exists as a diatomic element. So how then are we supposed to determine then the molar mass of this compound if we know the mass of one of a single atom? Well, this particular compound is made up of two hydrogen atoms. And so therefore, if you can only imagine, to find the mass of this compound, the molar mass of this compound, we take the mass of one hydrogen atom and we double it, because there's 2 hydrogen atoms there. So therefore, the molar mass of this compound here is going to be 2 grams per mole. Okay, and so that is how we then determine the molar masses of compounds. The molar mass of an element, we can get that directly from the mass number from the periodic table. We don't have to do any calculations to get that done. For the molar mass of a compound, all we have to do is add up the atoms that make up that particular compound. Okay, so let's go ahead and let's take a look at another example here. Okay, and so let's take a look at this compound here. Okay, and so with this particular compound here, it's made up of 2 hydrogens and 1 oxygen. Okay, so with that said, then we're going to add up the total molar masses. We have 2 hydrogen atoms, each hydrogen atom with the molar mass of 1 gram per mole. But that's not the only; those are not the only atoms in this compound. We also have oxygen. And so we'll go ahead and add to this mass here, the total mass here, the mass of 1 oxygen atom, which is, rounded to the nearest whole number, 16 grams per mole. Okay, and so when you add all those up, the mole, you'll get 18 grams per mole as your molar mass of water, okay, of this compound here. So make sure you keep in mind, this is an element. This is one form of a pure substance. For the molar mass of an element, you get it directly from the periodic table. For the molar masses of compounds here, for these compounds, you just add up the molar masses of the individual atoms and you'll get the molar mass of the compound itself. So that ends up being very straightforward and not very difficult. Okay? All right, so in order to find that out, that's what I pointed out to you, just calculate those masses. Okay? And so therefore, we would get then, what we obtain at the end of that calculation is the mass of 1 mole of the particular compound. So we're trying to find the mass of 1 mole of a compound, and we can do that by just adding it up. Okay, so let's go ahead and try this here. Okay, so we did hydrogen, H2, we did H2O. Let's find the molar mass here of hydrogen peroxide, which has the formula H2O2. Okay, so with that said, then we have 2 hydrogen atoms. The molar mass of 1 hydrogen is 1 gram per mole. Okay, we're going to add to that now 2 oxygen atoms, which has, each oxygen atom has a molar mass of 16 grams per mole. And if you add those together, then you get a molar mass then that is 34 grams per mole for hydrogen peroxide. And it's that simple, and trying to find these molar masses. Okay, so this then is the mass. Make sure you understand what this number is telling us. It's telling us that if we have 1 mole of hydrogen peroxide, that will be exactly equal to 34 grams of hydrogen peroxide. Okay, and you need to make sure you keep this in mind, because as we go forward and we do conversions with these, that's what this molar mass tells us. Okay, so let's go ahead and let's do one more real quick. Okay, and then I'll give you a chance to practice this, and then we'll finish up here. Okay, so let's find the molar mass of sulfur trioxide. Okay, so sulfur trioxide. So we first of all, we take the mass of 1 sulfur atom. Sulfur has a mass of 32. 1 sulfur atom has a mass of 32 grams per mole. To this mass here, we're going to add the mass of 3 oxygen atoms, and each oxygen atom has a molar mass of 16 grams per mole. You add all those together, you get a total molar mass for sulfur trioxide of 80 grams per mole. So that's what we have right there. And again, what this means then is that if we have 1 mole of sulfur trioxide, and if we weigh it out, we'll get an exact mass of 80 grams of that compound. Okay, so that's what this molar mass tells us about this compound. Okay. All right, so what I'd like you to do, and we'll finish up here on your paper, and this will be the only assigned problem that I'll have for you. Nothing from the book today, but this will be the problem that you'll turn in as the last problem. Find the molar masses of these compounds here, and then what we'll do is we'll start with this problem tomorrow. I'll give you the answers for these, and then we'll continue on, and we're going to use the molar masses of these compounds to do conversion. Okay. All right. So get this done, folks, and I will see you tomorrow, or hopefully, if you can, drop by the Zoom tutorial session this afternoon from 3:15 to 4:15, or whenever we have, or however long we have to go, and then I'll see you then. Okay. All right. I'll see you folks soon.